Hi, I'm Cyril Eric Tulio and I'm here to report about noise. What is noise? Noise is any unwanted form of energy tending to interfere with the proper and easy reception and reproduction of wanted signals. Noise is any undesired voltage or current that ultimately ends up appearing in the receiver output. And here are the results of noise: hiss or static, snow or confetti, bit errors, and signal loss. Here are the kinds of noise. Correlated noise. Correlated noise are mutually related to the signal and cannot be present in a circuit unless there is an input signal and is produced by a nonlinear amplification. No signal, no noise. Harmonic distortion are any unwanted harmonics of a signal. Intermodulation distortion. Intermodulation distortion are the generation of unwanted sum and difference frequency when two or more signals are amplified in nonlinear device. Uncorrelated noise, present regardless of whether there is a signal present or not. External noise, generated outside the device or outside the receiver circuit. Internal noise, generated within the device or within the receiver circuit. Here are the types of external noise. Atmospheric noise. Atmospheric noise are naturally occurring electrical disturbances that originate within the Earth's atmosphere. Extraterrestrial noise consist of electrical signals that originate from outside the Earth's atmosphere. And types of extraterrestrial noise are solar noise and cosmic noise. Solar noise are directly from the sun's heat, while cosmic noise are from the stars. Man-made noise produced by manufactured equipment such as automotive ignition systems, electric motors, and generators. And here are the types of internal noise. Shot noise. Shot noise are caused by the random arrival of couriers at the output element of an electronic device. Transit time noise shows up as a kind of random noise within the device and is directly proportional to the frequency of operation. Thermal noise are associated with the rapid and random movement of electrons within a conductor due to thermal agitation.
Hi, I'm Alessa Glendavid. So, for the noise power is the measured total noise in a given bandwidth at the input or output of a device when the signal is not present. So, in the formula, the average noise power is proportional to the absolute temperature of the conductor and to the bandwidth or spectrum of the thermal noise. So, Pn stands for the noise power, then T for the temperature of the conductor, B for the bandwidth of the noise spectrum, and K for the Boltzmann constant, which is 1.38 times 10 raised to negative 23 joules over Kelvin. So, for the noise voltage, consider the circuit below for the noise source equivalent circuit. For maximum power transfer of the noise source, RL is equals to Rn and VL is equals to Vn over 2. So, Pn is equals to Vn over 2 squared all over Rn equals to Pn, or for shortcut is equals to Vn squared over 4Rn. Since Pn is equals to TBK is equals to Vn squared over 4Rn. So, solving for the noise voltage, we have Vn is equals to the square root of 4K times T times B times R. So, Vn is for the RMS noise voltage, R for the equivalent noise resistance, T for the temperature of the conductor, and B for the bandwidth of the noise spectrum. So, RMS noise voltage due to several sources. We have here is the series combination. For the series combination, we have Rnt is equals to Rn1 plus Rn2 plus 2 more subscripts that could be given. Same with the voltage, which is Vnt is equals to square root of Vn squared 1 plus Vn2 squared plus Vn squared to raised to n. So for the parallel combination, we have the 1 over Rnt is equals to 1 over Rn1 plus Rn1 over Rn2. And for the voltage, V is equals to square root of Vn1 squared plus Vn2 squared. For power spectrum density or noise density, the average noise power per hertz of bandwidth. A figure that determines the amount of noise contained in a specified bandwidth. So, NO is equals to Pn over B is equals to K times T. NO stands for the noise density, then Pn for the noise power, then bandwidth of the noise spectrum for B. So, signal to noise ratio. It is a relative measure of the desired signal power to the noise power. The formula is S over N equals to PS over Pn. So, the S over N is the ratio of the power. In decibel form, we can say that S over N is equals to 10 log PS over Pn or equals to 20 log Vs over Vn.
핸드폰을 훔친 도둑을 구해줬다. 보통 죽도록 해줬다가 더 자연스럽죠. 네, 112죠? 여기 해성병원 응급. Oh, every time I see you, 그대 눈을 볼 때면 자꾸 가슴이 또 설레어와 내 운명이죠. 세상 끝이라도 지켜줘.
I'm Rihanna Mariel G. Victorio, and I will be reporting noise figure. Noise figure is a number by which the noise performance of an amplifier or a radio receiver can be specified. The lower noise figure, the better performance. Noise figure can be derived by taking the SNR at the input, dividing SNR at the output. Or 10 log F is equal to 10 log input signal power over input noise power over output signal power over output noise power. For an ideal noiseless network, F is equal to 1 because S over N of an input is equal to input of this network. Input signal power over input noise power is equal to output signal power over output noise power. So F is equal to 1. For a network that produces noise, input signal power over input noise power is greater than output signal power over output noise power. So F is greater than 1. Reactance noise effects. The significant effect of reactive circuits on noise is their limitations on frequency response. The equivalent bandwidth to be used in noise calculation with reactive circuit is BEQ is equal to pi over 2 B3 dB, wherein B3 dB is equal to half power bandwidth and BEQ is equal to effective bandwidth. Equivalent noise temperature. Equivalent noise temperature of a system is defined as the temperature at which the noise resistor has to be maintained so that by connecting this resistor to the input of a noiseless version of the system, it will produce the same amount of noise power at the system output as produced by the actual system. So, to get it, TEQ is equal to TO times F minus 1, wherein TEQ is the equivalent noise temperature in Kelvin, and TO is the reference absolute temperature, which is 220 Kelvin, and F is the noise factor. Noise due to amplifiers in cascade. Fisk formula. Overall noise factor of n stages. FEQ is equal to F sub 1 plus F sub 2 minus 1 over G sub 1 plus F sub 3 minus 1 over G sub 1 times G sub 2 plus F sub n minus 1 over G sub 1 G sub 2 times G sub n minus 1. Overall noise temperature of n stages. TEQ is equal to T sub 1 plus T sub 2 over G sub 1 plus T sub 3 over G sub 1 times G sub 2 plus T sub n over G sub 1 times G sub n minus 1 times G sub overall noise resistance. REQ is equal to R sub 1 plus R sub 2 over A sub 1 squared plus R sub 3 over A sub 1 squared plus A sub 2 squared plus R sub n over A sub 1 squared times A sub 2 squared times A sub n minus 1 squared. Shot noise. Shot noise is a form of internal noise which is due to the random variations in current flow in active devices such as tubes, transistors, and diodes. So, to get it, I sub n is equal to square root of 2 BIQ, wherein IN is equal to noise current RMS, Q is equal to change of an electron, which is equal to 1.6 times n times 10 raised to negative 19C, and B is bandwidth over the noise is observed, and I is equal to DC bias current in the device.
Hi, I'm Ruela Christine L. Panganiban, and I will be discussing some sample problems. First, for an amplifier operating at a temperature of 30 degrees Celsius with a bandwidth of 10 kHz, determine the total noise power in watts and decibels. Okay. Given the Boltzmann's constant, 1.38 times 10 raised to negative 3 joules per Kelvin, and the temperature of the conductor, 303.15 Kelvin, and the bandwidth of the noise spectrum, which is 10 kHz. So, computing for the noise power, we need to use the noise power formula, which is E sub n equal to K T B. The answer will be 4. So this is the total noise power in watts. To convert it to decibel, from the previous lesson, we need to use this formula. And the answer would be 103.78. Next, determine the noise current for a diode with a bias current of 20 milliamperes observed over a 30 kHz bandwidth. In determining the noise current for a diode given a bias current of 20 milliamperes and a bandwidth of 30 kHz and the charge of an electron, which is 1.6 times 10 raised to negative 19 coulombs, the noise current should be computed using the noise current formula, which is I sub n is equal to square root of 2 BIQ. Therefore, the answer is 1.856 times 10 raised to negative 8 amperes. Compute the noise figure of a receiving system with the noise temperature of 150 degrees Celsius. To compute for the noise figure, we need to use the noise figure formula, which is equal to 10 log F. However, we are only given the equivalent noise temperature, which is 423 Kelvin. But we can compute for F using the equivalent noise temperature, which is equal to TEQ times T sub O times F minus 1. So F is equal to TEQ over TO plus 1. So substitute the reference absolute temperature is always 290 Kelvin. It is equal to 2.4586. Then we can use this value to substitute it here. The answer is 3.9069. Last, what is the noise voltage when the equivalent noise resistance is 1 kilo ohms, the bandwidth is 4 kilohertz, and the temperature is 80 degrees Celsius? To compute for the noise voltage given the equivalent noise resistance, which is 1 kilo ohms, and the temperature of the conductor, 353 Kelvin, the bandwidth of the noise spectrum, 4 kilohertz, and the Boltzmann constant, which is 1.38 times 10 raised to negative 23, we need to use the formula for the noise voltage, which is Vn equal to square root of 4k Vr. Substituting the following. The answer would be 2.7918 times 10 raised to negative